Hey everybody, this is Larry. This is me going over week 4 of the weekly contest 237. Find XOR sum of all pairs bitwise n. So this one, actually a lot of people end up getting it, maybe. So hit the like button, hit the subscribe button, join me on Discord. Let me see. So now we're about, when I'm recording this, about 38 minutes into the contest, and you already see 440 accepted. So this is a little bit on the easy side, but it's still a tricky one because it is XOR. So I've seen this about every video, but the key thing about these bitwise operations, and not all the times, but once you can see that this is XOR, which is bitwise obviously, and a bitwise n, then the first thing I would think about is that every bit is independent of each other. And what do I mean by that, right? What I mean by that is that, and this is my code, no spoilers, please. That means that, let's say I have an array. Let's take a look at, say 1, 2, and 3, right? Again, we can just break it down bit by bit. So for example, in this case, let's just do the 0th bit. Whoops, this is 1. 0 bit, and then the 1 bit, first bit. I don't know if that's right, but yeah. So basically, you could break down each problem into its components, because this is just 1 times 0, 1 plus 0. 2 is just 1 times 2 plus 0, and so forth, right? So this is just like bitwise stuff, and the reason why we do this is because now we can solve each subproblem independently, because there's there's nothing to do, right? The first thing, obviously, well, the second thing, maybe the first thing, I don't know. I think I looked at it and I go, okay, n squared or n times m is probably, it's definitely too slow, obviously. I guess that is actually the first thing I did, but it's a Q4, right? So I didn't actually look, because I was like, it's probably going to be too slow. I think I took a peek. You could watch me solve it after the contest next, so that you could kind of see how I actually did it. But yeah, but now that you kind of break it down to the bit components, then now the question is, let's say, let's ignore the other bits, right? So now you have, array 0, which is just 1s and 0s, array 1, I mean. And then, you have another, you have another one, which is array 2, which is also just binary numbers. Again, because we do every bit independently, and then combine them later, we can only think about these binary numbers, right? And then the question is, then it becomes a lot easier, right? Because now you're trying to figure out, okay, you have a 1. If this is a 1, then how many if this is a 1, then what does it mean, right? You can kind of write it in a naive way, for x in R1, for y in R2, you have XOR x and y, yeah. So you have, wait, what? I forget which way it goes. Oh, you do the n. Whoops, sorry. So we do the n, right? And then now we have k as you go 0, say, and you just have, we XOR this by the x and y, right? And of course, that's fine. But how do we rephrase it another way, right? So this is like the brute force way, and this is going to be too slow because it's n times m. So then what you want to do now is kind of ask yourself this, right? Well, there are two things. One is, how does this function operate, right? Well, this is just equivalent to how many times we do we have x and y equal to 1, or maybe x equal to 1 and y equal to 1, if even number of times k is equal to 0, if odd number of times k is equal to 1, right? So, okay, so now looking at that, we can actually just keep track, now we could take the loops out of each other, right? Because now we're just saying, okay, for each x, you can say if x is equal to 1, then you do this thing, yeah, you could do this thing, right? Because if x is equal to 1, and if y is equal to 1, then x, then we flip the k value. And then now, now we can notice here, well, how many times does this happen, this flipping? Well, this happened exactly the number of times y is equal to 1, right? So then now, you could say, I mean, I'm using a really bad shorthand, but yeah, so yeah, so now this is just equal to if the number of y is equal to 1 is even. Well, what does that mean? If the number of y plus 1 is even, that means that you flip it even number of times. So then k is equal, then nothing changes, right? So k, you flip it to 0, and else, you flip it from 0, because y equals to 1 is odd, you flip it to the thing, right? So that's basically this idea for each bit. And then now, so now you can also replace this. Obviously, this doesn't do anything. So then the number of y is equal to 1 is odd, right? Because then now you flip the k. And we do this for every one. So then now you ask yourself, can we, in a way, can we cache or, save the number of calculations for this, right? And the answer is, of course, if you're looking here, then the answer is yes. Then we just basically have a count of is equal to, let's say count is equal to 0 for y in R2. If y is equal to 1, we do count, we increment by 1, and then now this becomes easier, right? Then now we just do if count is odd, which of course is just something like this. And yeah, and this is pretty much it. That's basically the idea behind this problem. So you could do this bit by bit and then combine them later. And then we'll go over our code. Basically, because of the bitwise nature, and you can actually do this in like another for loop, over 32 or something like that, if you have trouble with doing them in parallel the way that I did it. But the idea is exactly the same, which is here. This is my code that I did during the contest, and you could watch me solve it live next. Is that for each, I guess this is why we're using the same notation, but for each number in array 2, we look at the number of offset, and we just count the number of offset. And you can actually just mod it by 2 as well. But then yeah, so for the offset that is in that position, this is just a count. And then now this is the answer we have at the end. For each x, we basically we check this recurrence again, and then we just XOR it. Of course, and if this looks a little bit yucky to you, definitely, I'm not going to go over it too much because it is bitwise operations and it is a prerequisite for this problem. So I would recommend you get to understand how to read this per se, but that's basically how I do it, one at a time, for each offset at a time. Cool. And I think you can actually probably optimize this a little bit more, but yeah, but I did it during the contest and it was quick. So yeah, let me know what you think. Oh yeah, let me do the time first. So now the time is, given, let's say this is n and this is m, this is just going to be, time is going to be O of n plus m, because we just go for both of these arrays, so it's going to be n plus m times 32, which is let's just say the log of the size of the universe, which in this case is 10 to the 9th. I think you could actually go down a couple as well, but I do choose 32 just for consistency. So as your word size or your int size gets bigger, it will grow. But otherwise, it's going to be all of n plus m. In terms of space, it's going to be that same constant, which is 32, or O of 1, or O of log u, where u is the biggest number or something like that. So yeah. Let me write it down. So space is going to log of u, log u, where u is u is the biggest number, and time is O of n plus m times log u. Also, again, u is the biggest number, and n and m are the two arrays. That's all I have for this problem. Let me know what you think, and you can watch me solve it live during the contest next. That was a mess. Really gave away a lot of time. Odd. XOR sum of all the ends. And I spent way too much time in the last problem. Now I'm getting stuck on this one. So 1. So, okay, we just do a bit. I mean, it's not so hard. It's just that I'm trying to rush it. So, trying to do a bit at a time. So, this number of times. I wish I didn't spend so much time on Q3. Hey, yeah, hope you enjoyed that explanation or video. Hit the like button, hit the subscribe button, join me on Discord, join me on Twitch, whatever you like, join me on Instagram, I guess. Yeah, I'll see you next time, but stay good, stay healthy, and to good mental health. Bye-bye.